Dalton's law of partial pressure.
Hey everyone, have you ever wondered how the pressure of a gas mixture works? Well, today we're diving into it. Dalton's law of partial pressure. This law helps us understand how each gas in a mixture contributes to the total pressure. Let's identify what Dalton's law of partial pressure is, with some help of my members who have great insights for you.
Dalton's law, also known as the law of partial pressures, is a fundamental principle in the study of gases and their behavior. This law states that the total pressure exerted by a mixture of gases is equal to the sum of the pressure that each individual gas will exert if represented alone. In other words, the pressure of each gas in a mixture is independent of the pressure of the other gases and acts as if the other gases are not present.
This principle has far-reaching implication in a wide range of fields, from atmospheric science to industrial chemistry, and it's even prevalent in the field of respiratory care. Dalton's law can be mathematically represented with the following formula. P total equals P sub 1 plus P sub 2 plus P sub 3.
Mixture of gases, each gas exerts its own pressure on the container, and the total pressure of a mixture is simply the sum of pressure of each individual gas.
One of the most important applications of Dalton's law is in the field of respiratory physiology, where it is used to explain the behavior of gases in the lungs. The air we breathe is a mixture of different gases, primarily nitrogen, oxygen, and carbon dioxide.
Therefore, understanding the behavior of gases in a mixture is crucial for the safe and efficient operation of gas storage tanks, pipelines, and other equipment.
Dalton's law is a fundamental principle in the study of gases and their behavior. This principle has wide-ranging application in a variety of fields, including respiratory physiology, atmospheric science,
And industrial chemistry, and is a crucial concept for anyone studying or working with gases.
Let's say we have a container with three different gases, gas 1, gas 2, and gas 3. Note that the gases are all inside the same container. This means that they all have the same volume. Now let's take the same container and spread the gases out equally while holding the volume constant in each container. The sum of the partial pressures of the three gases will equal to the total pressure of the mixture of gases. Let's look at the pressure meters above the gas chambers to notice that each partial pressure of the individual gases equals the partial pressure of all the gases in the same container. Now let's look at the formula for Dalton's law of partial pressure. First, let's derive the ideal gas law where pressure times volume equals nRT. We can see that the pressure is equal to nRT over V. Now let's look at the partial pressure where at a constant volume, we can add the partial pressure to the individual gases to equal the total pressure of the combined gases.
Now, let's go to the concept of partial pressure and mole fraction. But first, what is a partial pressure? Partial pressure is the pressure exerted by an individual gas in a mixture of gases. It's the pressure the gas would exert if it occupied the same volume alone. While mole fraction is the ratio of the number of moles of a particular gas to the total number of moles of all gases in the mixture.
Calculating total pressure from component gases. To calculate the total pressure of a gas mixture, you can use Dalton's law of partial pressure. This law states that the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the partial pressure of the individual gases. method to calculate total pressure. Using partial pressures directly. If you know the partial pressure of each gas in the mixture, simply add them together to find the total pressure. Here's an example. A container has three gases. Gas A with a pressure of 2 standard atmosphere, gas B with a pressure of 3 standard atmosphere, and gas C with a pressure of 5 standard atmosphere. The total pressure is pressure total equals 2 standard atmosphere plus 3 standard atmosphere plus 5 standard atmosphere equals 10 standard atmosphere. Calculating partial pressure of a single gas in a mixture. Using Dalton's law of partial pressures and total pressure. If you know the total pressure of the gas mixture and the partial pressures of all the other gases, you can find the partial pressure of the gas in question by subtracting the sum of the known partial pressures from the total pressure. Here's an example. A container has a total pressure of 10 standard atmosphere. It contains nitrogen with a partial pressure of 3 standard atmosphere, oxygen with a partial pressure of 2 standard atmosphere, and an unknown gas. Partial pressure unknown equals 10 standard atmosphere minus quantity of 3 atmosphere plus 2 atmosphere equals 5 standard atmosphere. When a gas is collected over water, it becomes saturated with water vapor. The total pressure of the collected gas is the sum of the pressure of the gas itself and the vapor pressure of the water. To find the pressure of the dry gas, you need to subtract the vapor pressure of water from the total pressure. Problem. Suppose you collect hydrogen gas over water at 25 degrees Celsius. The total pressure of the gas collected is 760 torr. The vapor pressure of water at 25 degrees Celsius is 24 torr. What is the pressure of the dry hydrogen gas?
A few moments later.
Kinetic molecular theory of gases.
Kinetic molecular theory of gases. Postulate 1. Particles in motion. Gases are composed of a large number of particles, atoms, or molecules in constant random motion. Those particles move in a straight line until they collide with each other or the walls of the container. This motion is continuous and chaotic with particles moving in all directions.
Collision. The collision between gas particles and the walls of the container are elastic. An elastic collision means that the total kinetic energy of the particles remain constant. Energy can be transferred between particles but no energy is lost. These collisions are responsible for the pressure exerted by the gas. Negligible volume. The volume occupied by the gas particles themselves is negligibly small compared to the total volume of the container. In other words, most of the volume of a gas is empty space. This assumption is most valid to low pressure and high temperature when the particles are far apart.
No intermolecular forces. There are no attractive or repulsive forces between gas particles. Particles move independently of each other without influencing each other's motion. This assumption is most valid for ideal gases. Real gases do experience intermolecular forces, especially at low temperature and high pressures.
Relationship between temperature and kinetic energy. The kinetic molecular theory establishes a direct relationship between the temperature of a gas and the average kinetic energy of its molecules. In the context of the kinetic molecular theory, the pressure exerted by a gas is a direct result of the collision of its particle with the walls of the container. Here's the details explanation. Origin of pressure. Gas particles are in constant random motion. As they move, they collide with each other and the walls of their container. This collision exerts a force on the walls. Pressure as force per unit area. Pressure is defined as the force exerted per unit area. In the case of a gas, is the total force of all particles collision divided by the area of the container walls. Pressure equals force over area.
Explanation of pressure in terms of particle collisions. Number 1. Gas particles in motion. Gas consists of numerous tiny particles that are always moving randomly. They zip around in straight lines until they bump into something. Number 2. Collisions with container walls. These gas particles constantly collide with the walls of their container. Each collision exerts a tiny force on the wall. Number 3. Pressure as the result of many collisions. Pressure is the total force from all these collisions spread over the area of the container walls. More collisions or stronger collisions means higher pressure. Number 4. Factors affecting pressure. More particles. More gas particles in the same space mean more collisions, thus higher pressure. Higher temperature. Higher temperature makes particles move faster. Faster particles hit the walls harder and more often, increasing pressures. Number smaller space. Squeezing a gas into a smaller space makes the particles hit the walls more often, increasing pressure. Now, think of it like this. Imagine throwing a ball at a wall. Each ball exerts a small force. The more balls you throw per second, and the harder you throw them, the greater the overall force on the wall. This force spread over the area of the wall is like gas pressure.